Hello and welcome to Electronics. My name is Fatima Garba Yusuf, and today we are going to talk about the degree of freedom analysis as well as solve an example. Now the major example that we're going to solve in this video is this that you are seeing. But look a bit complicated, but when we explore what degree of freedom analysis actually is, or what the number of degree of freedom actually is, then it will be easy for us to just come back and solve this question. As you can see from the question, we're asked to calculate the number of degree of freedom at the first one is point E, which you can infer that it's actually the equilibrium point where the faces all coexist. And then within the region of A plus L, both A and L are actually phases, and then within the region A plus B. And as we can see in this phase diagram, we can assume that pressure is maintained at a constant value while we have a plot of temperature against weight percent of the two different phases. As you can see, this plot is similar to a binary phase diagram plot, so we can infer that we have two components, and actually the number of components, number of phases are quite relevant in this calculation of the number of degrees of freedom. So before we move to calculate this, it's important for us to revisit what the degree of freedom actually is and the parameters we will be needing to solve this question. Hence, what's the number of degrees of freedom? To answer that question, we can say that the number of degrees of freedom is the number of independent intensive variables needed to define the thermodynamic state of a system. As we all probably know, in thermodynamics or in material science, we often have independent variables and dependent variables. So for you to completely define a system, you have to have some independent variables. Now in this case, if your degree of freedom is 0, it means that the system is completely well defined and you don't need any independent variables to define that system. And typically the independent variables we are talking about at this point will probably be pressure, temperature, and typically in these cases the independent variables we are referring to are temperature and pressure. So for us to solve any question pertaining to these kinds of binary calculations of degree of freedom, we are going to use a rule that is called the Gibbs phase rule for non-reactive systems. And it goes thus: for you to calculate your number of degrees of freedom, which is represented by F, you have to equate it to C minus P plus N. And usually N could be 2 or 2 minus 1. 2 minus 1 is 1. So in some cases, you use your N to be 2, and in some cases, you use it to be 1. But then what's C, what's P, what's N, and how do we get them from this diagram? So our F, as I mentioned earlier, is the number of degrees of freedom. Our C is the number of components. That is, if it's a binary plot, you already know that your number of components is supposed to be 2. Then the number of phases refers to the total number of phases that are present in the system. For example, in a Unary system, we can have liquid, vapor, and gas, but here, as we can see, we already have some labeled phases. Then your N is the number of non-compositional variables that are present, that are already defined. So, and the reason why in some cases N could be 2 and in other cases it could be 1 is because in some cases you have both values of temperature and pressure. That is the reason why you have your N to be 2, and in some cases you can have only 1. That is, you could either have temperature or you have pressure. However, before we move towards solving these binary question we have, how about we visit an example of a simple unary phase diagram calculation of the number of degrees of freedom. So here is an example. As you can see, it's similar to the diagrams we looked at when we were having an overview of phase diagrams. And this is a phase diagram for the water system. So it's important for you to note that in calculations for phase diagrams, you don't really need much information, especially if you're just calculating the degree of freedom. Just by looking at the graph, you can actually determine your parameters. Now in this case, if we're using the Gibbs phase rule, our F is supposed to be equal to C minus P plus N. So in this case, our F is our unknown variable, while our C is the number of components. And since this is a unary phase diagram, it contains only one component, which is water. So our C is 1. As our phase P, you can see our three phases. We have ice, solid, we have our water, liquid, and then we have water vapor, which is the gaseous or the vapor phase. So we have three phases. As for our N, so you can check out how many defined independent variables do we have. Now this will differ based on the position that you are calculating the degree of freedom for. So for example, if we take our point O for example, then our defined parameters will be P and T, because we have defined parameters for pressure and temperature at this point. Hence, our N will be equal to 2. Alright, so in this case, our F, let me label this at O. Our F will be equal to 1 minus 3 plus 2. And this will give you minus 2 plus 2, which is U. And this makes sense because in this position O, we don't need any additional information or independent variable for us to define the system. We already have the pressure and the temperature, so it's already defined thermodynamically. As for the other regions, such as this area along the line B, in between the water vapor region and the solid region, some of the values will change. So in calculating your degree of freedom, your F will still be equal to C minus P plus N. But in this case, let's say along B, in this case, your C will still be equal to 1. We only have one component, that's water. And then your P will be two phases, because two phases are coexisting at this point. While your N will be 2 also in this system. So in calculating our F, we'll have 1 minus 2 plus 2. So in this case, our degree of freedom is 1. So I hope you get that. Now I just did this so that we could see how this kind of question is solved in a unary phase diagram situation. Meanwhile, we are going to solve our initial question, which asked us to calculate the number of degree of freedom at point E, and then within A plus L, and then in the region A plus B. So here again, we are going to define our formula, which is F is equal to C minus P plus N. Here, however, our number of components is going to be 2. As you can see, we have our pressure as a constant value, just as was seen in two component systems, while we have a weight percentage given. This implies that there's not just one single component that's. Meanwhile, our components will be constant, while our P will depend on the position where we are calculating our degree of freedom. So in this case, we are going to start with point E. And here, our component C is equal to 2. And the reason why this is equal to 2 is because this is a typical diagram of a binary phase diagram. As we can see, we have been given the weight percentage of just one component here. But for you to get the other one, you simply minus 50% from 100% to get the other one. As for the number of phases at point E, we have our number of phases to be. As for the phases at point P, at point E, as for the phases at point E, we have our number of phases to be 3 because it's the point of equilibrium, right? While our n is going to be equal to 1 because we just have one independent variable contained in this graph. We only have temperature, right? So our n is equal to 1. So our calculation will be F is equal to 2 minus 3 plus 1, which will give us 0. And of course this makes sense because it's the point of equilibrium. As for the two other points, A plus L, or two other regions, A plus L and A plus B, both of them have their P to be equal to 2. Hence, our F for both regions will be equal to 2 minus 2 plus 1, which will give us 1. It means if you define your temperature, then you'll be able to calculate your pressure. There is one independent variable that is needed for this system to be fully defined. So with this, we've come to the end of this video. Look out for the next video where we are going to solve a question that doesn't even showcase a phase diagram, but you'll still be required to calculate your degree of freedom. So see you in the next video. Thank you for watching.